so we have been discussing cryptands and its different variations. So, in my last class I touched upon self persistent organic cages, which I could not finish. So, here I am meanwhile I was able to write this organic cage. Okay. You can see that this particular organic cage is quite rigid. Okay. This binding site is very rigid. It has some flexibility on this side, but this particular site is very rigid. So, this is the difference between self persistent organic cages and cryptands. Cryptands are flexible, they can wrap around a metal ion well, but this particular molecule, this looks like a cryptand. You will say, why you call it a different name? Well, there are subtle differences. This subtle difference here is that these donors are very somewhat rigid, so that whether a guest is in or out, they are not going to move around, unlike a cryptand. So, these things are very came into prominence very lately, 5 years or 10 years back, and they are also extremely important, a subcategory of say cryptand, or some people do not like it to be subcategory, but it is an organic cage, okay, 3-dimensional structure. So, I will not go into any controversy. So, I will say that it is an self persistent organic cage structure. So, we have done cryptands, we have done tryptophans or cyclophans, and this is self persistent organic cages. Self persistent organic cages, they can be really big, cavity can be really big. The reason being that the bridgeheads are aromatics. Okay. Bridgeheads are aromatic. Once the bridgehead is changed to say nitrogen, it will be quite flexible, but it is being an aromatic, it will be quite rigid. All right. So, that is the difference between self persistent organic cages and cryptands. Their bridgeheads are always, or in most cases, their bridgeheads are aromatics, and they are very good. Their cavity is very large, because the bridgehead is large. Bridgehead, if it is a big, bridgehead is big. So, therefore, their cavity is also big. Let me draw a cartoon and then explain. If the bridgehead is big, therefore, their cavity also will be quite large. If the bridgehead is small, sometimes, then this is a cryptand. Okay. So, it is not bad. So, it is being big, we is able to put metal nanoparticles inside and can bring about excellent chemistry with metal nanoparticles, and once they are in, they will be very stable. Some other self persistent organic cages, I can write cartoons, I cannot write the structures. They can be not necessarily they will be like shape of a cryptand, but they can be like this. They can be like this. Okay. they can be like this, and there are, you can imagine many structures. Only thing you have to understand that whether a guest is in or not, their shapes are not going to change. That is why they are called self persistent organic cages. Okay. So, after that, now I will come to another type of molecules, that is known as spherands. Spherands. Spherands means sphere basically. Okay, let me draw a picture first. Unfortunately, I have to draw to make you understand. Okay. One, two, three. I have to draw 6. I have drawn 4. This is 5. And then okay. So, 1, 2 and 3, these are all aromatics. Let me write this way. Okay. All right. So, these are methyl groups. All right. So, this is a very rigid structure and looks like a sphere. Why? Donors are sphere. This oxygen, maybe I will put a different color. This oxygen and this oxygen. That means alternate 3 are up and other 3 are down. So, because they are up and they are down, that means a 6-membered spherand will be perfectly octahedral oxygens. Oxygens are octahedral transposition. So, it can, when a metal ion can go inside, it can be make a very facile complex, this Spherands. Okay. So, whether an 18 okay, and they are very little solvated. So, this is the Spherand, simplest Spherand, but there are some other derivatives are also there. Let me draw that. There is a difficulty is involved, but I will draw. It must be a bigger one. Okay. Hmm. 1, 2, 3, 4, 5, 6, not here. Okay. All right. It can be a structure like, I am just writing different kinds of spherands. O, 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 okay, and then OME. So, different. So, this is another spherand. So, I am not going to discuss so many things, but this is a spherand molecule and they can accept, they are very rigid, they are not going to change any, they are also self persistent, size, okay, size persistent. It is not self persistent, it is shape persistent. This should be shape persistent. Okay. This is shape persistent, not size self persistent. This is also shape persistent systems and they can capture metal ion inside the cavity. In this case, where we have all OMEs, then it will be a 3 OMEs are up, oxygens are up and 3 are down in a trigonal antiprismatic fashion. So, they can easily form octahedral metal complexes. How to synthesize them? That is kind of difficult, but still let us see. You take aromatic bromo-aromatic compound, reacted with butyl lithium, then you can get, it will get a lithium derivative, and then you can put iron ACAC Fe SeSe, FeSeSe is a template and it can form AR-AR bonding. Okay. So, that is how AR-AR bonding diaromatic can be formed. So, we do it here, we take bromo, OMe, this compound, and from there we can get OMe, Br, and it can continue. So, this is the way we synthesized spherands. Okay. So, now we, that means we have completed this kind of cryptands, cyclophanes and shape persistent organic cages and now spherands. Now, let us start something else. Now, we will show you another structure. You might be wondering why I am trying to give you different kinds of structures in this class. The reason is these supramolecular synthons will be later useful. Okay, we will use them later to have interesting systems. Okay, to tackle a phenomenon, we need different types of molecules, and these molecules are, that is why these supramolecular synthons can be made to form supramolecular species. That does not mean non-cyclic compounds, aliphatic or aromatic, they are useless, not that. They will be in addition to these cyclic structures, all right. So, all these things will be obvious as we go along. So, now another type of compounds we will discuss, Cucurbituril. So, these kind of compounds were synthesized serendipitously, not that they design and all that. Okay. what happens, first we saw one previous lecture that phenol and formaldehyde can lead to bakelite, and when it is unsubstituted, when the phenol is unsubstituted, then phenol formaldehyde resin called bakelite will form polymeric species. But when it is substituted in the para position, then we can get calixarenes. So, similarly here also we take this one diuride compound, okay, is a bis-uride glycouryl. Let us write it. NH NH What is this compound? Bis-uride. There is a urea moiety here. Bis-uride glycoluryl. Okay. How this is formed? This is formed as a product of glyoxal and urea. So, you said you take glyoxal, is this, glyoxal and urea. Okay. C double bond O and NH2. So, urea and then urea. Urea, all of you know urea. So, if you cook them together, you can get bis-uride glycouryl. Now, if we react this with excess aldehyde, okay, so it is really very funny way of making this, plus excess CH2O formaldehyde, excess formaldehyde you reacted with this under acidic condition, water plus HCl, then you get a precipitate PPT, you get a precipitate. That precipitate you treat it with concentrated sulfuric acid, heat it up to 100 degrees Celsius, okay, heat it up to 100 degrees Celsius, and then you get a solution, a clear solution you will get. So, you take bis-uride glycouryl and take excess formaldehyde under water and HCl, and we heat it. Then you get a precipitate. That precipitate dissolves in concentrated sulfuric acid if we heat it at 100 degree Celsius. You should be very, very careful when you make this kind of materials. Okay. And then if you add, so you have a solution now, a sulfuric acid solution of a clear solution, you dilute it with water, lots of water you put and cool it to 0 to 10 degrees Celsius. That means, you put it in an ice bath, then what happen? Still is a solution. So, you have an acidic solution of this product, and what happens? When you lower you allow it to settle, you can slowly evaporation will lead to Cucurbituril. So, Cucurbituril is a very interesting way, and it was done first in 1905. This synthesis was achieved serendipitously, but even then it was revisited in 1980s. But even now this is synthesized here, synthesized like this. You take bisuride glycoluryl and react it with excess formaldehyde. Under acidic condition, you get a precipitate. Okay. But in concentrated sulfuric acid, under hot condition, you get a clear solution. All the precipitate dissolves, and when you again dilute it, you dilute it and leave it in an ice bath, you leave it, slowly Cucurbituril comes out, and comes out like a white solid powder. Okay. They are very, very pure. Now, the question is, usually you get a mixture of Cucurbituril. There are, and Cucurbituril, let me draw the picture first, which I cannot draw because it is very difficult to draw for me, but I will explain. Let me explain, not this. Cartoon will not do. So, you have nitrogen, this nitrogen, and all these nitrogens are tertiary amide. Okay. Double bond O, right, double bond O, and where is it come? Where it comes? This saturated. One, two, three, 4. Okay. My drawing is not very good looking, but काम चलाओ. Okay. In all cases. So, it goes on like that. Now, I can draw how does it look. Okay. So, this here, what is the characteristics now? All the nitrogen are tertiary amide, and tertiary amides are insoluble in water. So, not only in water, in most this particular cucurbiturils are insoluble in all solvents. They are soluble only in concentrated sulfuric acid, and then when you add water, they will have they will be precipitating out. okay, except, all right, let me first draw it. Now, I can give you a cartoon variety of that shape. Shape is like this, double bond O, and here also. What I have drawn we will call Cucurbituril 6, Cucurbituril 6, okay. So, 6 membered and it looks like a pumpkin. We know what is a pumpkin looks like. So, it is look like a pumpkin and this is we call CB within bracket 6. Why 6? Because 1, 2, 3, 4, 5, 6 on either side is 6 and inside is also only we have all the valencies are satisfied, no unsaturation, nothing. So, nitrogen valency is satisfied, carbon valency is satisfied, is all single bond and is very, so inside is hydrophobic in nature. Inside is hydrophobic, inside hydrophobic and outside is hydrophilic. Hydrophilic because of this oxygen. So, this is the characteristic structural features of Cucurbituril 6. It has at the entry it has hydrophilic and inside it is quite hydrophobic. It is very interesting. Suppose I want to suppose I have a and the distance or this cucumber, okay, the distance between here. So, distance from here to here is such that 4 carbon chain, carbon, 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 okay, it can go inside, it can go stay inside and then if you have a NH2, then NH2 can make hydrogen bonds with this on the either side. So, this is the structural features of Cucurbituril. We will be using this Cucurbituril for some work. Okay. For example, the diameter, the width vary from C5 to C8 between 4.4, for C5 it is 4.4 and for CB8 is 8.8 angstrom. So, it varies widely, all right, and for 6 is therefore in 6 it is about 5 point something angstrom, all right. So, I completed this. Next time I am going to do something known as cyclodextrins and that will be almost, we are coming almost at the end of describing these materials, their structural features and then we will use them one after another as we progress. Then you will know why I am taking so many lectures describing this kind of compounds. So, today I stop. Thank you.